Okay, thanks, Matt. Okay, so we are talking about entanglement, topological defects, maybe more precisely tensor networks and topological defects. So yesterday we talked about, I meant to get a lot farther yesterday, but as these things go, also lots of questions for which I'm very grateful, so keep asking questions. Yesterday was sort of the background of why do we care about these tensor network states, why are they interesting, how are they used in many-body physics. And we started talking about classification of phases of matter, trying to use these tensor networks as a guide. These things have been useful both in computation, so they are very powerful variational methods, but what we focused on more yesterday is this theoretical aspect behind these tensor network states. What are the symmetries of these tensor network states? How can a matrix product state be symmetric? What are the different ways in which it can transform under symmetry? And from that we learned something about classification of phases of matter in 1 plus 1D. And after that we moved on to one dimension higher, to this 2 plus 1 dimensional case. We talked about these PEPs, which are the 2 plus 1D tensor network states. And we arrived at this condition yesterday. So we were saying that in contrast to the 1 plus 1D case, in 2 plus 1D, you can have these tensor networks, these 2D tensor networks generated by this 5-valent tensor A here, with these non-trivial symmetries on the virtual entanglement degrees of freedom. Right? So I want to talk a bit basically about this equation. The whole of today's talk is going to lead up to what are possible solutions to this equation. So if you just stare at this, if I give you some random tensor A, it is very difficult to find solutions to this equation. This is a bit similar to what Zohar was saying yesterday, that if I give you some Hamiltonian, it's very difficult to find what the possible symmetries are if they are of this generalized kind. And this is a similar problem. So rather than doing that, I want to talk about a way of constructing explicit solutions to this equation, starting from what we know about topological order and lattice models and TQFTs and that kind of stuff. And doing that, we already will gain a lot of intuition about what kinds of structures you get in these equations. But before I do that, I have to define basically what these kinds of objects are and what all the possible equations are that they will have to satisfy. Right?
Can I just ask a basic question?
Yeah.
Are you anticipating sort of fixing an A and then trying to find symmetries that obey this? Or looking for certain A's that obey symmetries?
So we will write down the consistency conditions for these kinds of symmetries and then basically figure out what the mathematics is behind these consistency conditions, what the mathematical structure is, and that will give us all possible A's that commute with this for free. So it's basically like what you know for a finite group. If I give you a finite group, you know that a symmetric Hamiltonian has to be built from Lebesgue coordinate coefficients. That's the only thing it can be built from. That's the only symmetric operators. We will do something similar here. So we will figure out what these symmetries are described by and what their Lebesgue coordinate coefficients are. And how we can systematically construct Hamiltonians, or in this case, 2 plus 1D tensor network states that commute with these symmetries.
Your A is a proxy for a Hamiltonian.
Yeah. Well, okay, I will... Jumping ahead a bit, I'm talking about 2 plus 1D topological systems here, but you can think of the boundary theories of these topological systems, which will then inherit the symmetries of this thing. But that's sort of for the third lecture, if I maybe I'll get to some of that today, but that's supposed to be third lecture. Yeah.
Sorry,
yeah.
It looks just a little bit like Jan-Baxter equation, but it's nothing.
It's not entirely unrelated, of course. It maybe looks a bit more like Jan-Baxter because I use the 4-valent tensor here. Really like the more elementary equation would be, and that's actually the one that I'm going to use, would be something like, I have a 3-valent tensor like this, and I have OA, going to this. So this is sort of this is a more minimal version of this equation, because any tensor like this, I can sort of split it into 2 tensors that are trivalent like this. So this is actually the elementary equation. Now this doesn't look like a Jan-Baxter equation, but this looks like a pentagon equation. And in fact, that's exactly what it will turn out to be. So that's what I'm building to. Okay. Yes?
There is a horizontal to A and another is a vertical to A.
Right, I should be using...
Does it make any sense to ask if the horizontal one to be a different one?
Right, so I should be using different colors here in these. So these two lines, let me label the virtual lines of this thing in red. This is a convention I will try to stick to throughout the whole thing. So these red lines and these white lines, they need not be of the same type. They can be different kinds. Is that your question?
Those two OA have to be the same. Can it be OA and OE?
No, so this operator here, in fact it's really this line that's labeled by A. So this runs all the way through. So this will be some topological defect labeled by A and it runs all the way through. Like these operators themselves, so these white lines, they can differ. It's like having a different representation for every leg. But it will label one single.
But you could consider some defect.
Yes, although if you want those to be such that the insertion point doesn't matter, those things being simple objects, there will not be anything other than the identity that commutes with it. But you can fuse these kind of lines together. That's what we'll talk about now. So I want to write down what are the conditions that these operators OA have to satisfy. I will just write them down, and then we will look at them a little bit, be confused, and then I'll explain how to construct solutions to those equations.
Will this string eventually relate to the string operator in the Lam1 model?
Yes, but not one-to-one. So the string operator, I'm jumping ahead a little bit because you know these things, but the string operator in Lam1 is labeled by the center. This is going to be basically the condensed version of that string operator. So there will be some choice of boundary conditions, and there will be some functor from Z of C to some other Morita equivalent category D, and that will be what this thing is labeled. But you know too much already. So.
Sorry,
Yeah.
could ask a really dumb mathematician's question again? I'm only asking now because of the way of
No, that's okay.
if the total space of physical states is V,
Yes.
my understanding here is that there's an auxiliary vector space W,
Exactly.
and A is the map from W tensor W to W tensor W tensor B. Is this right?
Yeah, that's correct.
Okay.
Yeah.
Thank you so much.
No,
Very helpful.
I mean, there's different ways to think about it, right? You can move these W's to one
Sure.
side or the
I
other. You
realize
can
it.
think of it as a map from W tensor W tensor W tensor W to the physical space,
Sure, you can do that too.
as a map from virtual to physical.
So
But
what I said is exactly correct.
it's exactly correct. But it's good that you pointed out here, because here, okay, I will think of it later. I will think of it as a map from W to WV, and that will be useful for what we say later. So thanks for the question. Okay, any more comments? Okay, good. So let's have a look at these operators and let's see what kind of properties they have to satisfy. So 1. MPO algebras. So the starting point is these kinds of operators, these OA, because it's kind of annoying to keep drawing the OA. I will now just draw them like this. And then draw a line through them like that, labeled by A. So let's assume that this is something on closed boundary conditions. So this is the same as that. So imagine whenever there's a crossing here, imagine there's a tensor OA. Something. It just gets really annoying to keep drawing. So we have these kinds of operators. Let me call it O. Call this OA, which is, I know, confusing because I've used it as the local tensor as well, but I hope it's clear from context what I mean. And let's say that you have one of these operators, and you have another one, OB, and it's clear that the product of these two things will also be a symmetry of this thing, right? I just pull one through and then the other, right? So it's natural to impose that these things are closed under multiplication. So that if I take an OA times an OB, I get something like a sum over NABC of OC. Now I should put a superscript L here, where L is the number of sides. And so for now, This NEBC is just some random complex number, right? I haven't told you anything about it. Now, very suggestively, I did use capital N. It turns out that you can show, and I will not do it here, but you can show that if you want this to be true for all L, then these NABC have to be integers. Positive natural numbers, positive integers.
So these always are supposed to encode some symmetries of the ground state, right?
These are these operators that I'm defining on. I'm taking closed loops of these operators now, and I'm considering the product of these operators.
Right. But these are representing some symmetry.
Yes, they are the symmetries of the entanglement degrees of freedom of this 2 + 1 dimension.
Right. So I should think of the labels as being like good group elements.
Exactly, yeah. So one example would be where this is just a group. Or generally, this is going to be a fusion ring. And that's how we will end up with these fusion categories.
Sorry, why L matters?
Because there's other kinds of matrix product operators that just close as an algebra, but where this structure constant that you get for that algebra would depend on the size of the operator.
So you have to fix L.
So this requirement that I want this to be the same algebra, irrespective of L, is what makes these symmetries kind of topological. It gives them some sense of scale and variance, right? It doesn't matter. And that's what I want, because I want to be able to move this operator freely through my tensor network. And as I move it through the tensor network, the number of virtual legs on which it acts will change. But I don't want this to affect the underlying algebra, or well, in this case, fusion ring. And so that's why I'm posing this for all different. Okay, good. So, from what we talked about yesterday, if you look at this equation now, and you write it out graphically, say something like this, I have an A, I have a B, and I'm saying, okay, this is equal to a sum over C, N, A, B, C, times this operator now labeled by C. The reason these have to be integers is basically because these are direct sums and you can only take integers for direct sums. It's sort of related to comments that Zohar made yesterday. So if you look at this equation and you think about what we talked about yesterday, this fundamental theorem of matrix product states, it follows that we can think of this operator as a state if you just think of all these. So this is really now an operator. We can just fold the codomain of this thing into the domain. Think of it as a vector. So here you have some matrix product state. Here you have some matrix product states, and I'm saying they are equal for all L, right? From what I told you yesterday, you can infer from this that there is an invertible transformation that will relate the tensor that's generating this state to the tensor that's generating this state, right? So there exists some X, which graphically basically satisfies this. X, let me see, it's -1 here, doesn't really matter. It should be red. This is A, B, C, C. So this follows from this theorem that we talked about yesterday. The fact that this tensor, if I think about it like that, and this tensor here, are generating the same operator, or state, it doesn't really matter, for any system size, means that this tensor and this tensor must be related by an invertible transformation X. Right? That's what we talked about yesterday. I didn't prove that theorem, but it's not hard to prove. So, by having this global multiplication property, using the theory of tensor networks, you can derive the fact that there exists something that will locally implement this multiplication. Okay. Now, you can look at this thing here. Okay, I can put it to the other side as well, which is maybe going to be useful for later. So I can put it here. Yes, I just took the inverse of that thing. Now, I can look at what happens if I multiply 3 of these operators together. And if you do that, you will find that there are 2 inequivalent ways to locally decompose this, right? You could first, so if I consider the product of 3 of these MPOs, like this, I could first decompose this one, compose these guys, and then compose these guys. So this would be A, B, E, C, D, or I could do it the other way around. Like this. A, B, C. And okay, what I again will not prove, again it's not hard, but it would take up too much time, is that these 2 situations are related by an invertible transformation, sum over f of f, A, B, C, D, E, F. So this is again just using these tensor network techniques, you can prove that these tensors here, which you can just derive, given these tensors you can derive the existence of these. This is just a linear problem for this thing. You can construct these 2 tensor networks here, and you can figure out this F symbol here. And now this F symbol, anyone who's ever seen anything about fusion categories knows that this thing has to satisfy a pentagon equation, and it defines a fusion category, right?
I'm sorry, I'm a bit confused.
Yes.
Is X completely invertible?
No. Okay, that's
Okay.
a good point. So it's invertible on the subspace spanned by the contraction of these 2 tensors here.
Okay.
Which is
So it is a projection.
yes.
Oh.
Yes. I mean, for a given set of labels A, B, and C, it is a projection of A and B going into C. It's like a Krepke coefficient. If I then sum over C, then it is basically spanning the full space. There are some caveats to these things, which are details I'm happy to go into after the talk. But just to sketch sort of where we're going, I would like to stick to this. Okay.
Sorry,
Yeah.
I'm very slow, but so this OAs,
Yep.
in my previous convention, these are operators from W to W.
Yes, so from a tensor product of WWWW to WWWW. So these are all living on these W
The
auxiliary spaces.
tensor products. Also.
Yes, yeah.
Okay.
Because you have to imagine this living in a very big
Sure.
network, right? And it
Sure.
should be able to move around freely, things like that, right?
Okay. But, and this equation that you started out with is implementing the fact that these are symmetries.
Yes, exactly. That's what it means for them to be symmetry. There's something that commutes.
I think I understood that, but all these other equations are also coming from physical considerations somehow.
So these are saying that, okay, if I have an operator that commutes with this,
Right.
let's say I have some set of them.
Sure.
The products of these operators will also commute with these things. So there's some algebra structure in
Sure,
there,
yeah.
right? If I'm just looking at the set of operators. And now I'm looking at these algebras, so I'm multiplying these things together.
Mm-hmm.
And I'm requiring that this algebra is the same for any system size. I
Oh,
need that.
see. Okay, I see.
I need that if I want to be able to freely deform this thing through my lattice.
Yeah.
And then this requirement turns these guys into integers. And then, okay, just the fact that these multiply like this gives me the existence of these fusion tensors, we call them, which will satisfy this condition and from which I can get this F symbol. Right? So this is kind of the way we fell into all this, right? We didn't start out wanting to study fusion categories or TQFTs or anything like that. We just started from these consistency conditions. We wanted to understand matrix product operator symmetries. And just via these tensor network tools, you are forced to consider these kinds of equations, these kinds of F symbols, pentagon equations, and everything that comes with it. Right? So that's kind of the way we got to this point.
And the objects now of the fusion categories are these labels.
Exactly. So they are the simple objects of the fusion category. And okay, I didn't say that I'm assuming there's a unit, that there's duals. tools you get by requiring that these matrix product operators are close to undertaking the dagger, and so all these kind of things. But that's extra structure that I don't want to go into. There was a question there, yes.
Relation between the diagrams you were drawing on the top board and what you're doing now,
Between this one and this one?
or even just like your
Oh, and the first
line
one?
with the dashes.
So these are the same diagrams, right? I've just omitted drawing the tensors O here at every crossing. So at every crossing, imagine they're sitting one of these tensors here. It's just a shorthand notation. The A here?
The
Oh, well, I'm just considering these operators by themselves now, right? They still commute with this A, these operators. So this operator and this operator is the same thing. I'm saying that, okay, there will be operators that commute with these symmetries, but let me just look at these symmetries by themselves for now, right? Let me just study what these symmetries look like, what their structure is. And then we will go on to construct the A that commute with this thing. This is like in group theory, right? You first study the properties of the group before then finding out what the representations are, what the Klebsch coordinate coefficients are, those kind of things. So it's similar to that. That's the kind of logic that we're following. Okay. So I've arrived at these fusion category structures, and I would like to know now, how do I construct solutions to these equations? How do I find these matrix product operators, and subsequently, how do I then find the operators that commute with them? Right. Hopefully you can see that once I know these matrix product operators, solving for the operators that commutes with them is kind of easy. This is a linear problem in A, right? So once I know the symmetries, I can just figure out its commutant, so I can learn about what the possible symmetric operators are. Whether I think of those as Hamiltonians or whether I think of those as tensors building up some 2 plus 1D state. So what I want to do now is really just try to explicitly construct solutions to this equation. So for that, inspired by the fact that these things arise as symmetries of models with topological order, we're going to look at models for topological order in 2 plus 1 dimension.
Solve it where x is your input, or?
Yes, more or less, yes. It's in a very, very indirect way, and I will not talk about it, but it is basically that. So what you can do is, given this f here, you can construct all the x's that are compatible with it. Then given those x's,
You're interested for the other way around, I see.
yeah, but the way you actually mention it is actually the way that we do it in practice. So you give these f's, you give me these x's, all possible x's. I can then construct all the possible matrix product operators that will satisfy this identity here. Which is weird because this is not a linear problem. Nevertheless, it's some representation theoretic thing and you can actually do it. And then given those, you can construct the operators that commute with it. But it's really this that we are doing. We are studying the kind of representation theory of these fusion category symmetries on the lattice. That's the kind of thing that we're going to. And so, yesterday I already mentioned that in the case that this is a group, for instance, this F symbol here could be something like a 3-co cycle, and this is what we would call an anomalous symmetry. It would be anomalous for the theory living on the boundary. So as Zohar said, anomalies are something when you have group multiplication rules, but only up to a phase. In this case, you have this local associativity, but only up to a phase, and that's a hallmark of anomaly, and it's something that people are interested in. Okay, good.
And in this context, let's make that following. These operators should be sort of line operators.
Exactly, yeah. Okay, so I have to talk about topological models in 2 plus 1 dimensions. So these are basically 11 models, or string net models. Now I'm assuming most of you have encountered these in some form, so I'm going to be rather quick about this. If you have more questions, or I'm happy to answer them after the lecture, or you can just look at the original references. I think they're quite readable. So I want some Hamiltonian. So we're going to kind of take this was the motivation for looking at this, right? We will end up back here, hopefully, but for now we're going to look at these 11 models. So I'm interested in having some Hamiltonian, let's say some local Hamiltonian, sum of terms I, j, h, I, j, that exhibits topological order. Now, there's a very simple example of this. It's called the Tory code. It's been around since quite some time now, which is basically a model of qubits. It's something that I'm assuming most of you are at least somewhat familiar with. And then there's several generalizations of this Tory code. Tory code is something that's based on a group Z2. You can do this for general groups. Then you get these what's called quantum doubles. But you can even generalize this further into something called stringnet models or Levin-Wen models, where the input you take for these kind of things is a fusion category, a spherical fusion category. So I'm interested in figuring out a kind of Hamiltonian of this form, because if I have a Hamiltonian of this form, it's local and I will be able to define tensor network representations for it, because of what we said before. So what I need is a spherical fusion category. And let me just call it C. So we already saw in Niels' lecture what a monoidal category is, or at least he talked about it. So a fusion category, spherical fusion category, is a monoidal category. So there's some kind of notion of taking tensor products, C going to C. There's simple objects, which I'm going to denote as x1, x2. These are simple objects. So this is just some choice of representatives for the isomorphism classes of simple objects. I'm just going to call them simple objects. There is a unit, so there's a1, which satisfies x, then so 1, 1, x, x. There is an associator, so there's something f, x1, x2, x3, which does this, x1 tensor, x2, is like this. And then we have these morphisms of Hom spaces of x, let's say xi going to xj. And these are, well, either this is empty if I different from j, or it's the complex numbers if I j. So if these are simple objects, right? For the simple objects, this is true. So the Hom spaces of this category are complex vector spaces. Of course, there's a very nice graphical calculus for all these things. I'm sure we will, well, you've kind of encountered it in the context of Frobenius algebras in this lecture. So the way we work with this graphically is, say we have some x1, x2, x3. I will read these diagrams from top to bottom, just to keep you on your toes, I guess. So this is how I denote a vector, a basis vector for the Hom space of x1 tensor x2 3. This is an element in this Hom space. So this vector space is living here at this vertex. And then in this graphical notation, you can express this f symbol as follows. So x1, x2, x3, x4, x5, I, j is the sum over x6, j, well, of f, x1, x2, x3. I, j, k, l of this diagram. X1, x4, x5. Right? This is all very, very standard, so I'm going rather quickly over this. And then this f symbol here has to satisfy a pentagon equation, which you can derive by looking at the two inequivalent ways of going from this situation to this. So either you first do an f move to end up here, and then it's another f to end up here, or you take the long way around and then you go like this, this to equation you get from this schematically looks something like F is F, right? So that's the pentagon equation. And this is something that, well, basically defines your fusion category. So one way to systematically classify fusion categories is to look at these fusion rules, which, okay, I see I didn't define. So at the level of simple object, this is x1 tensor, just in case, sum over 3 and x1, x2. One way to numerically look for fusion categories is to find consistent fusion rings, and then check whether for those fusion rings you can find a solution to the pentagon equation. If you can, then you've got a fusion category. If not, then this fusion ring is not categorifiable. Very quickly, I want to give basically two main examples of this thing. So one option is the category of representation of a group, in which case your simple objects are irreducible representations, which I'm going to call J, because I'm thinking about SU2 in the back of my mind. You've got fusion rules for these things, which is just the tensor product of representations, which you know. One thing I didn't say, I assumed that this was spherical, so there's also a notion of dimension for these objects, quantum dimension, which basically graphically amounts to kind of taking the trace of these objects. This gives you a quantum dimension. Quantum dimension of is just the dimension of this representation. And then, okay, you've got an F symbol for these things.
Question.
Yes?
So, which condition said this is a spherical?
Oh, spherical means that I've got some rigidity here. I've got duals. I've got a evaluation co-evaluation, so I can define a left and a right trace, and then spherical means that these coincide. So normally you would have like a left dimension and a right dimension, and spherical means that if I put these pictures on a sphere, you can turn one trace into the other, and so spherical means that those are the same. That's what spherical.
That implies D must be real number.
Yes, yes. So these are unitary fusion categories also. So this is also for any unitary fusion category. It's a real positive number.
I thought this can be positive or negative or something, depending on which model you are interested in.
So for a unitary, there is always a choice that makes them positive.
But for StreetNet, is that necessary? Like I thought to get double Stamion with.
Oh yeah. So that's you're cheating then. You're saying you're absorbing the Frobenius-Schur indicator into the quantum dimension. So either you say, I require everything to have positive Frobenius-Schur indicator, which is useful in computation, because then you don't have to keep track of it, but then your quantum dimensions are negative. But the proper way to do it, in general, is to say, I have positive quantum dimensions, and I have non-trivial Frobenius-Schur indicators. And then, okay, the associator here, let me just write it down. So this F symbol here is just the 6J symbol, so J1, J2, 3, 4, 6. This is the 6J symbol that people know in representation theory. Another example is Vec G. Let me include an omega here. So here your simple objects are, so this is the category of G-graded vector spaces. The simple objects of this are one-dimensional G-graded vector spaces. I'm just going to label these by group elements. G1, G2, G3, in, Vec, G, omega. All the quantum dimensions are 1. And then your associator, so F, G1, G2, G3 is just G1, G2, G3, which is an element of H3 of G versus U1. So the multiplication rules are really just a group multiplication here, and then the associator of this thing is this 3-co cycle, which we already encountered. I went rather quickly over this because I'm assuming a lot of these things are known. If you have questions, feel free.
For naive people. So you went from X to J. These are representations or?
Yeah, because I'm talking about representation of a group and the prototypical example.
One X
everyone
is just the abstract.
Here X is just some simple object in a category.
Okay,
So
so
it
you
have to
want,
be coming from rep G, and in fact in this case it doesn't come from rep G. So here I'm calling these simple objects G, because that makes
what's
sense.
G from J to G?
So here I'm thinking of J as representations of the group, and the monoidal structure is taking tensor products of representations. That's not group-like in general. We know that a spin 1/2 times a spin 1/2 is a spin 0 plus spin 1, right? That's not group-like fusion. Here I do have group-like fusion. So here it's just G1 tensor G2 is G1 G2.
Thank you.
And then I can put an associator on here as well, so I don't have to do that. I can make this trivial, and then I just get vec G. But I can add this associator into here, and then I can describe something more complicated than that. That's related to these anomalous symmetries that we also.
Sorry, could you say just once again what is vect WG?
So this is the category of G-graded vector spaces.
G-graded.
The simple objects are one-dimensional G-graded vector spaces, which I just denote as their group elements. The tensor product is basically the respects the group multiplication structure, right? And I'm saying that I can choose a non-trivial associator on these guys, because this satisfies the pentagon equation, because the pentagon in this case just becomes a tricocycle conjugate.
And that W is the superscript.
Exactly, this W here is this W. I need not put it here, but I just did it because so this, with this I can now define a Hamiltonian that will exhibit topological order, namely the Levin-Wen Hamiltonian. So let me considering the following situation. I have a Hilbert space. Let me say I'm working on a hexagonal lattice. I draw a hexagonal lattice. I label all these edges by simple objects in 6, x, 7, doesn't really matter, x, 9, 10, 11, 12. And then here I will have these multiplicities, so I1, I2, I3, I4, I5, I6. And then I'm considering the Hilbert space spanned by the direct sum of all these x and over all these I. So I'm basically looking at all possible configurations that I can make of this kind. That is the Hilbert space on which I'm going to be defining my Hamiltonian. And so the Hamiltonian itself on this Hilbert space is going to be a sum minus the sum over some vertex term, which actually is going to be redundant in this case, times some packet term. So what is this vertex term? So okay, two things that are important. These terms, this model is going to be exactly solvable. Why is that? It's because all these terms commute. This B, P, B, B prime is A, B, prime, sorry, A, B, B, 0. So this Hamiltonian is a sum of commuting projectors, which makes it trivial to find the spectrum of this Hamiltonian, right? You just can simultaneously diagonalize all these terms, and then the spectrum is just adding up the eigenvalues of all those individual terms. So this is an easily solvable Hamiltonian. Now, this vertex term, what it's doing is it's basically enforcing the fusion rules at every vertex. Now, the way I've constructed my Hilbert space, this is sort of true by definition. It's a little bit tricky to properly define the Levin-Wen model in such a way that you really have a proper vertex term, as that you may be used to in Tori code. If you don't know what the Tori code model is, that's fine, you can ignore this comment. But actually, so in this case, I really don't need this vertex term. What I do have is this plaquette term, and the way this plaquette term works is by, I can define its action on, let's say, a plaquette, like this. So X as follows. So defined by taking this configuration, I'm drawing it as a vector, which is maybe a bit confusing, and inserting a loop labeled by x. And then using the rules that I have there, and there's one rule that I didn't really draw, which is that
Sorry, Lawrence, I just missed it. So for dropping these A terms from the Hamiltonian, this is redundant somehow when you pose the fusion rules.
I'm only working in a Hilbert space. The reason I'm saying it is because also in the Levin-Mann paper, this plaquette term is only defined in this Hilbert space. So this plaquette term only has support in the subspace where this one is satisfied anyway. So this guy is redundant.
You put them as constraints, the A's.
Yes.
Then you work on the rest.
Yes, but the BP term is only defined in that subspace anyway. So even if I don't include it, this guy will project into that subspace anyway. And then you have to work a bit to, if you want to define the plaquette term for the Levin-Mann model outside this Hilbert space where AV is satisfied, you have to change some things. That's true already for the original Levin-Mann model. This is just to contrast it with Tori code, where this is not true. We have a proper vertex term and a proper plaquette term, and they both do different jobs. Here this is not true. Here everything is done by the plaquette term. The vertex term is not doing anything. In the original Levin-Mann construction. There's a way to modify it, but I'm not going to talk about that. Finish the comment I was doing. So just one rule I didn't say is that these home spaces that form an orthonormal basis for these things. So if I have two parallel lines like that, I can decompose them.
You mean I don't get vertex excitations? In
You
the
still get
Levin-Mann?
okay, it's difficult to talk about vertex excitations in Levin-Mann, in a generic Levin-Mann model. If I take something like Fibonacci, there are excitations that you can neither call plaquettes or vertex excitations.
Sorry, I can have a deal, but I have a vertex excitation. I mean, I can't constrain.
Yes. Yeah, all I'm saying is that that vertex excitation won't be characterized by violating this, it will also violate this because this guy is only defined on the space where.
That's what the information you need is already in the B, but you need the A's. You can't say I just remove it from the Hamiltonian.
I'm saying that this doesn't change anything to this Hamiltonian. It doesn't change anything to the ground state or the excitation on this
I
thing.
disagree. I think the information you need is already in the BP, but you need it in the Hamiltonian.
Okay, I guess it depends a bit on how you're thinking about this. You cannot define, if you say this thing acts as zero outside its support, then I agree, then you have to add an AV to give energy to the excitation. But you can modify this thing in different ways to act outside of that subspace such that you don't need the AV. So what I'm saying is that on the ground state subspace, you don't need this guy. And then there's a question, which is not usually addressed in these kinds of papers, of how to extend the action of BP outside that ground state Hilbert space. And there's ways to modify it such that it basically takes over the job of this AV entirely, which is effectively, I mean, then I think then we're talking about semantics, right? Do we call that a vertex term or not? That's semantics, I think.
Yeah, thank you.
But this is a confusing point, that's kind of overlooked. So what I can do now is use this rule there to map this to, and I'm going to be a bit schematic. You can absorb this loop onto this plaquette, like that, using this resolution of the identity rule there. And then I can use 6 F moves to reduce it to this. So that defines the action of the plaquette term, well, of basically a plaquette term labeled by X, and then the actual BP of Levin-Mann, BP is the sum over X of dx BP X divided by the Frobenius-Perron dimension of the fusion category. So this thing makes BP into a projector, which are things that are easy to check just using the rules. Okay, so this is the Levin-Mann model, and this takes a fusion category and produces a model with topological order. Now we didn't say which topological order yet. For that you have to look at the symmetries of this Levin-Mann model. And that's these string operators that we already talked about. So what are the symmetries of this Hamiltonian? For that, you need something called the center of this fusion category. So the center, symmetries. So if you consider the center of C, which, if you don't know what it is basically objects Z, which are some direct sum of simple objects in C, together with something called a half braiding, which takes Z tensor, say x tilde, to x tilde tensor Z for all x tilde C, right? So this objects in the center, they are objects in the fusion category, not necessarily simple objects, that's why there's the direct sum here, that commute with every other object, but as usual, any claim about any statement at the level of objects in a category is always up to some isomorphism, and that isomorphism is called half braiding. So graphically, what this looks like is that you basically have something like this. So for every object x tilde, you can define this kind of thing. So this morphism, this half braid looks like this. So you have some object in your category, which is not necessarily simple, which braids with every other object in the fusion category. Now, the fact that this is a braiding means that this has to be compatible with all the other morphisms in your category. And so, in particular, has to be compatible with this. So what you find is that an equation like this here. x3, x1, x2. So these lines that are labeled by the center, I can draw these and I can basically freely push them through any other diagram that I can make in my fusion category. Right? That's what it means. This equation looks a lot like the equation that I drew over there. Right? That's not a coincidence, and that's kind of where we are going to. And so with this, hopefully you can see that the symmetries of this model are, let me say that I draw some configuration like this. Let's say that I have some line labeled by some object Z in the center. What this shows is that I can freely move this line wherever I want. So in particular, this tells me that the action of this line on this Hilbert space, which you can evaluate using explicit, so you can expand this morphism into the specific bases that I have there, and then you can put it onto this lattice using these F moves, just like we did for the plaquettor. So this gives you an action of this symmetry operator on this Hilbert space. But by this graphical calculus, I know that this will commute with my plaquette operator, because I can either first apply the symmetry, then the plaquette operator, or I can first apply the plaquette operator, which I can do by just pulling out the symmetry, push it away, apply the plaquette operator, push it back, and then evaluate it. So it commutes with this plaquette operator. That's the only term in my Hamiltonian. So this action of this symmetry operator commutes with my Hamiltonian. So these are the symmetries of the Hamiltonian. And so the topological phase of 11-man model, so this kind of symmetry is called a one-form symmetry. It's something that doesn't act on the global space, but it acts on a co-dimension 1 manifold, so it acts on strings. It's a string-like symmetry in 2 + 1 dimensions. Commutes with a Hamiltonian, and this is the thing that's broken in the ground state of 11-man. So the topological order in 11-man model is a one-form symmetry breaking phase, where the one-form symmetry is given by the center of C. So the topological order is described by the center. Because the symmetry is broken, you can build domain wall excitations from it, and these are what the anions are going to be. So if I, instead of considering the symmetry like this, I terminate the symmetry at some point in my model, this will be an excitation. Because the symmetry is broken, it's really like having a domain wall excitation. And so your excitations are also labeled by the center of C. Right? Your different ground states on a torus, if you consider this model like this, you can draw a little loop around the torus labeled by this object Z. For every object Z here, you will get a different ground state. So you get the number of ground states is given by the number of objects in the center of this fusion. Right? So this is the Levin-Wen kind of story, and what the symmetries of the Levin-Wen are. Are there any questions about this before I move on?
In this model, is it possible to more explicitly connect this Hamiltonian, which you have in sort of some quasi-closed form, to this A in the first order?
Rather, okay. I mean, this is kind of spoiler for the end, but yes, it will turn out to be somewhat connected. But I will get to this in the end. That's exactly right, actually. But, yeah.
Is it connected exactly to some A?
So these f's here that you're getting by evaluating the plaquette term will enable you to define what these a's are almost one-to-one.
In such a way that product state corresponding to A gives you a ground state.
Yeah, exactly. So the idea is that, this is what I wanted to say in the end, that because this is a commuting projective Hamiltonian, it's trivial to find a tensor network ground state for this, because the ground state of this thing is just defined by the product of all the projectors onto the +1 eigenspaces of all these terms. So if you take that operator, which is a tensor network operator, and act with it on any reference state, you will get a tensor network that is the ground state. So the expressions that go into this A will follow from the expressions of this packet operator. So that's the computation I wanted to do at the end. Okay, any more questions? Yes. Sorry.
So
yes.
if we take C to be a group,
Yeah.
It reproduces the the quantum double model for
Up to a unitary transformation, yes. It's not on the nose that, but almost.
Yeah, because if so X would be group elements, right?
Yep.
And then the BP.
Sorry, you have to take rep G if you want to.
Yeah, exactly. Because with rep G, then the BP becomes the projector onto the one group element, which is.
Yes. Yeah.
So yeah, we'd have to input rep G to get the.
Yeah, exactly. But the vec G stringnet and the rep G stringnet are connected by a finite depth circuit anyway, which I will talk about in 20 minutes. So it doesn't really matter at the end of the day.
Yeah. Okay.
Because they're Morita equivalent.
Okay, thanks.
Yes.
I'm trying to understand your notation for the sector. It looks like there's just Z is just one object.
No. So Z, it's all possible objects such that you can find a morphism that makes this thing commute with everything else up to this isomorphism.
All possible objects you can construct as direct sums of the simples?
So yes, for which this property holds.
I see. Okay.
So you just have a whole bunch of. Okay, there's also a notion of being simple here, right? You take a direct sum of objects in the center, it's still some object in the center, but then it's not simple anymore as an object in the center. So there's a finite list of simple objects in the center, which as objects in the original fusion category may not be simple, but they have to satisfy this equation. So the objects is basically, it's Z together with gamma of Z. For a given Z, there might be multiple solutions gamma Z, in which case there would be distinct objects in the center. So whenever I'm drawing a line like this and I say it's labeled by Z, really it's labeled by Z and gamma. This gamma is what I use to kind of evaluate this thing here. As an object in the category, which is what I need to, for instance, fuse it onto my original lattice, it's just some generically non-simple object in the category. Does that make sense? Right, let me make some space.
You are assuming that you have a semi-simple category.
Yes. Lots of these things have been generalized in various ways over the years, but those are complications I really don't want to get into. They are interesting, certainly if our end goal is trying to just understand symmetries of 1 + 1 Hamiltonians, and then a lot of the structure that you need to be able to define topological models, you actually don't really need it in the 1 + 1D setting. So non-semi-simple symmetries are fine. Sometimes you don't even need units for these kinds of symmetries, so there's lots of things that you can relax and still have them be consistent symmetries of 1 + 1 Hamiltonians without them really arising from this kind of construction. But this construction is kind of nice and well under control.
Maybe this is a good question, but so you chose a hexagonal lattice here.
Yeah.
It's going to have like particularly nice map.
No, it doesn't really matter. No.
So did you want to have trivalent junctions?
Yes, because any non-trivalent junction can be resolved as trivalent, so If I do it for trivalent, you know how to do it for anything else. It's just that these vector spaces, if I draw something like that, I have to tell you how I decompose it like this anyway, right? And then we're back in at the trivalent case. So this was the 11-1 construction done by Levin and Wen in 2006, and then some 6 years later, but I understand that you did a long time before that. Itaev and Kong, so Liang Kong, looked at possible boundary conditions for these Levin-Wen models. So what I did here is for closed manifolds, I can put a torus or a two-torus or a two-torus doors with two holes, but it has to be closed manifolds. So how do I find these models consistently in the presence of boundaries? And what is the correct categorical structure for these kinds of boundaries, right? So I forgot what number I'm at, 3, I don't know. S and with boundaries. Right. Cool. So if you kind of think about it, one thing I didn't draw here, something that these stringnet ground states satisfy is, the reason for this kind of construction is that there are the fixed points. You can retriangulate these ground state configurations up to a unitary transformation, where that unitary transformation is literally the F move. So for instance, you can have things like this is F times this. So whenever you have this kind of 4-valent junction here, you can resolve it in this way, or you can resolve it in this way, and it only costs you this unitary F move, right? So this is kind of a property of having this renormalization group invariance. Using this move and a few of the other moves that I talked about before, you can freely deform these stringnet configurations one into the other. So this is kind of a property of having this renormalization group invariance. From a quantum information point of view, this really allows you to define a quantum circuit and isometry that coarse grains these things exactly. So we want now the same thing, but in the presence of a boundary condition, right? So let me different color here. So what I want is these configurations to end on something. So now I'm going to color in a different way, such that you still get this kind of scale invariance property, but at the boundary. So imagine this blue thing as being a boundary. This is where my stringnet configuration ends on the boundary condition here. And I want this to be true still, where this is now going to be potentially some different F symbol, which I'm going to denote like this, the little triangle. You'll see why in a bit. So the question is, what is this mathematical structure? This is what's known as a module category. So if you have a fusion category, which is something that satisfies this Pentagon equation and these rules that I talked about, there's something called a module category, which graphically basically allows you to draw pictures like this. So more precisely, what is it? So given some fusion category C, say I'm given C, a module category, a left module category M is the following. It's a set of objects, so M1, M2, 3, and M. There's something called an action of this fusion category onto this module category, which is something that we note as this triangle. That's where this triangle comes from. Something that takes C times M, takes it into M. So at the level of the objects, this would be something like X acting on M1, giving me a direct sum of M2 of N, X, N1, M1, M2 of M2. And then there's this thing called a module associated, which we denote by this triangle F. That basically tells you how to take X1, x1 acting on, oh no, sorry, x2 on M. X2 on M. Right. So it's exactly the same as before. I've only replaced one of these objects here by something in a module category. Now this module category by itself is not a fusion category. There's no functor that takes M times M into M, right? It doesn't exist. So in that sense, it's something that's more general. Now, of course, any fusion category is a module category over itself. This is like the regular representation. A fusion category can act on itself, in which case these fusion rules just become the fusion rules of the original fusion category. This F symbol just becomes the ordinary F symbol, right? So there's nothing new there. But this is more general. There are more kinds of boundary conditions that you can consider. So one kind of boundary condition you can always consider for the string model is just terminate it and do the same as that you've been doing in the bulk. But the point is that there are other options. You can do more than this. Now, this equation here, this module associated, has to satisfy also a pentagon equation, so similar to before. This pentagon equation is now going to be a mixed pentagon equation. It's going to involve this F symbol here, but also the F symbol of the original category. And so, graphically, schematically, it looks something like this. It's very easy to derive, so maybe I'll leave it as an exercise. It looks something like this. So you've got two of these module F symbols here, one normal one, and then two normal ones here. So this defines a module. And then, okay, if you like, the action of the plaquette term in the presence of this boundary condition is BP that we defined before, X acting on, say, configuration like this now, where I have this boundary here, is really just the same as before, so draw, I do one too many, not really matter, like this, and then you insert this X here. And yeah, you evaluate it using these rules. So it's again the same. Using this rule, you can evaluate this kind of thing. So this gives you the action of this plaquette term in the presence of the boundary condition. If you were to do this for something like the Tori code, you would find that there's two possible boundary conditions. One is, so Tori code is built from taking Z2 as a fusion category. There are two possible boundary conditions. There are two possible module categories for Z2. It's itself, and then there's also one that's basically the category of vector spaces, so it's something with just one object. And then those would correspond to what people call the smooth and the rough boundary. Okay, so this was string models with boundaries. It's really nothing much changes. I could talk about boundary excitations and things like that, but I think Carolyn will talk about this a little bit more, so I'm going to leave that as it is. The only other thing I need now is domain walls, so I'm really going through all the names of this conference, which is good.
Sorry, did you need to say that BP is given by the same formula? That's not modified.
It's not quite the same. So the way you evaluate is the same. So you do this, you insert this, you do this resolution of the identity, and then instead of using 6 normal Fs here, you would use.
No, but the projector, I mean the construction of the projector BP in terms of BP axis.
It's exactly the same.
It's exactly the same.
Yeah, nothing changed there. And then indeed, so you just need to use 2 of these module F symbols here to evaluate. That's all. That's the only thing. Okay. Let me actually erase this. I want to talk about domain walls, so I don't really need this. So the final step of this is domain walls. Let's say that you're interested in taking 2 stringnet models, maybe defined with a different fusion category, C1 and the C2, and you want to glue them together in such a way that these RG properties are still satisfied. What do you have to do if you want to do that? So, take red as well. So, kind of the equation that you would write down for that is, well, you want this thing to be a boundary for one of the string net models. That's clear. You also want it to be a boundary for, so okay, you need this equation that we had before. This. You need a boundary for your other string net model, which I'm going to draw in red. You need something like this. This. So what you have is you have a fusion category C. Let me draw C in red. You have a module category M. I have another fusion category D. Right, so that's kind of my coloring for these kind of things. So M is a left C module category. Already messed up there, so I'll flip this round. Sorry about that. This used to be white. Right? So I have a M is a left C module category, which means that for the string net model C, M is a consistent left boundary condition. I have another string net model D. I'm saying M is a consistent right boundary condition. So M is a right module category, which is really the same thing as this. You just flip these things in the definition. And then the only other thing I need is that these two actions are compatible. So I also need something like this. I have this, this being isomorphic to this, and this. Right? So this here is the left module associated that's doing this. This thing here is the right module associated, which is the same. You just flip around the order of the arrow. And this thing here makes M into a bi-module category. So this is a bi-module associated, which we draw this little bow tie because it's both a left and a right arrow. Right. So all these things have to satisfy various Pentagon equations, which are very easy to derive. I'm not going to do that explicitly. So these kind of categorical structures are what describe domain walls between string models. Now, the only other thing I need is a notion of fusing domain walls together. So if you take two domain walls, let's say I'm in this configuration here. I have a C1, domain wall, C2, domain wall, some C3. And let's say that this domain wall is labeled by M1, this is M2. And there is something called fusion of domain walls. You can compute, you can basically squish these things together and think of it as a domain wall from C1 to C3. And this is something that, again, I will not really use too much, but this is given by, gives you a new domain wall, which you can explicitly compute, which is given by, well, it's the relative, so M1 both times C2, M2. So there's a notion of composing these domain walls because via the relative to the linear product, if you don't know what it is, it doesn't really matter. It's just some composition of domain walls that allows you to take these things together. And now this allows me to define what's called an invertible domain wall. So if I have some...
Sorry.
Yes?
The reason you're able to do this is because it's topological.
Yeah. So I have some boundary conditions, some other boundary conditions. I should be able to coarse grain this until it's gone and end up with a new domain wall. And so that's what this is giving me. I'm not defining mathematically what's going on there,
but just to make sure again, always I'm still keeping in mind the 2 plus 1 dimension.
Yeah, so this is a 2 plus 1 dimensional theory still. I just include 2 or 3 2 plus 1 dimensional theories together, and now I'm asking, okay, can I coarse grain or fine grain my way into other kind of configurations, and that's what's going on. So this allows me to now define what's called an invertible bimodule category, which is something like this. There's an M1 and then an M1. I'm going to know this M1 bar. denote it as M1 inverse or something like that as well. And so this thing here is an invertible bimodal category if there exists an M1 bar, kind of its inverse, such that this reduces to basically this situation, where I think of C as a bimodal category over itself. So kind of, if I have a domain wall such that there exists another domain wall with which I can annihilate it, such that it's gone, then we call this an invertible bimodal category. What this means at the level of the excitations is that if I have some excitation here, which as we saw before, labeled by Z of C, I have excitations here which are labeled by Z of D, and excitations here which are labeled by Z of C. For this to be consistent, imagine taking an excitation here and pushing it through this kind of composition of domain walls. What this is telling me is that nothing should happen to it because these domain walls, they've disappeared. So what this is telling me is that the excitations in Z of D and the excitations Z of C, they have to be the same. So having an invertible domain wall requires that the center of C is the same as the center of D. Because you need to be able to push excitations through a domain wall, right? That's the idea. So if you can push excitations through freely, it means that this excitation must survive here. It cannot just disappear. It cannot condense on this boundary, which is the other option that can happen. It must survive here so that it can get pushed through this again. So this isomorphism here is basically what's happening if you take an excitation here and you push it through. You can push it back, and so it's an isomorphism, it's something that can invert. That's what happens if you have an invertible domain. Okay? Any questions about this bit before I dive into the last part?
The location, what is that?
Z is the center, sorry.
The center.
It's this thing.
Yes.
So they are the symmetries of these models, but because this is a symmetry breaking phase, they also label the excitations of this model. So the different anions excitations, which have all these exotic braiding and whatever properties that we know, they follow from this center. Basically. Yes? Sorry. Yeah.
If you have an invertible bimodal category, is the inverse related to the orientation reversal of M1?
Yes, basically. So it's M op, basically.
Okay,
so it's almost exactly the same data, just reversed.
So if there exists an inverse, then it's M op.
Yeah, pretty much. I mean, yeah.
But if it's not vertical, M op still exists, but it just won't.
Yeah, it won't satisfy these things. So you can always define an M op, which is literally just flip all these things in the definitions, right? Yeah, exactly. Yes?
I'm trying to translate this into more used to my language.
Sure.
Do you mean ZG as some Drinfeld center or something like that?
Yeah, it's a Drinfeld center. It's the center, Drinfeld center, quantum double, all the same kind of thing.
Are you saying that if you have an invertible domain wall, then you don't want the quasi-particle inverse around?
Yes. Yeah.
Okay. Sorry, this is a very ignorant question, but could you explain again why won't you think of these as excitations?
Here I'm thinking of them as, so these are the symmetries of my model, right? They commute. And I'm telling you that this is a symmetry breaking phase for these symmetries. Now, if you have a symmetry breaking phase, your excitations are obtained by taking the symmetry and acting on a part of your system. And then at the endpoints of that symmetry, you will get an excitation. It's exactly the same. So in 1+1D case, if you take the easing model, you have a symmetry breaking phase. I don't know how much this will speak to you, but let's say that you have a state where the ground state is all spins up, and then your symmetry is just a flip symmetry. If you act with that symmetry on a part of your system, you will create a domain wall excitation, which are excitations that basically, because your Hamiltonian wants to align these spins, there will be a penalty when they are disaligned. It's very similar here. So here, this thing here where this thing ends, this will violate this. I mean, this will not be a +1 eigenstate of this BP term anymore. So it will violate the Hamiltonian, and you will get some energy. Only here, not here, right? Because here I could just freely move it out of the way. Here it commutes, but not at this endpoint.
So they give you excitations of these broken things.
Exactly. Yeah, exactly. Okay. Yes.
So how you dress your model there with the plus and minus spins?
Sorry, can you say it again?
You said in the icing case they should
yeah.
some change in the spin orientation of the bracket.
Yes, but that's in 1 plus 1D, right? So that's a normal zero form symmetry breaking phase where I have a global symmetry that's being broken, and I'm saying that, okay, we know that I can create excitations by acting on a part of my system, because this will create like a domain wall. So I will have all spins up, and then I will have all spins down, and at the point where they change, this will cost some energy in the Hamiltonian, because the Hamiltonian wants to align them, right? And it's exactly the same here. So the Hamiltonian wants these endpoints not to be there, basically, and then when you put this thing there, you get some penalty in the Hamiltonian, and that's an excitation. But it's a local excitation, because it's only violating, at most, this and this bracket term, not any other. That makes sense? Or?
Entirely, no.
I'm sort of, because we or many people tend to think of topological order as this exotic thing, but it's really just a symmetry breaking phase. It's the symmetries with respect to which it is symmetry breaking that are a bit exotic. But other than that, it's really all the same as a normal symmetry breaking phase. So we can use the normal intuition that we have about symmetry breaking phases. For the ground states, which are obtained by acting with the symmetry operators on one ground state, reference state, I can obtain all the other ground states. And for the excitations, which are domain wall type excitations. I think Liam, you also had a question on
since the Hilbert space only defined on vertices or edges,
yeah.
what do you mean by this
Indeed, so you have to, so this is only enough if I want to describe the ground state Hilbert space. If I want to extend this Hilbert space, then I have to add basically one extra degree of freedom, like this, to every edge. And this is also to do with how you properly extend the Levin-Wen mode to act with the vertex term. So, but you're right, you have to add this degree of freedom.
I see.
Sometimes you can get away with it and just completely absorb this thing into the other vertices here. That's fine, but generically, this is a cleaner way of doing it by adding these extra vertices. And that's the way you have to properly define the vertex terms and Levin-Wen to modify.
Or you can also do it along the edge.
Sorry?
You can also do the string, define the string order along the edge.
Oh, yeah, sure. So indeed, you can also just think of, so when I say evaluate the action of this, I really mean like, you can just do it like that. Just fuse it into everything and end up with some original configuration. That's also right. I'm saying that you can deform it like this and then absorb it, and then you're back in this original. Okay, good. That's
So far, you are mostly talking about non-chiral topological orders. Can you comment on which part can maybe generalize or different? Chiral?
Well, basically none of this, right? So there are no commuting projector Hamiltonians for chiral topological order, or at least we believe there are none.
How about your statement about symmetry breaking?
I'm not sure about that. Yeah, really, I'm too familiar with the story to make any precise claims about the chiral things. In terms of state sums, what we are doing, this is really like a Hamiltonian version of Turai-Viro. Formally, if you want to do chiral stuff, you can do this Rishkin-Turaev thing, which I don't think has a, well, it doesn't have a state sum construction, so it's no real lattice version of it, so I don't really want to, I don't want to say things that may be wrong, so I'll just leave it at that. Okay. So the final thing I want to say now is how to construct tensor network representations for these string net ground states that I just wrote, which you can do as follows. So one thing I told you here is that if I have a C and a D that are connected by an invertible bimodular category, then the center is the same. So the excitations are the same. Basically, it's the same topological order if C and D are connected by an invertible bimodular category. The technical way of saying this is that C and D are Morita equivalent. So if C and D are Morita equivalent, I get the same phase. Now, all the way in the beginning, the first lecture, I mentioned that phases are defined by things that can be connected by constant depth quantum circuits, right? So the natural question is, if C and D are the same, is there a constant depth quantum circuit that connects them? And the answer is yes, and it's very easy to construct using these invertible bimodular categories. So what you can do is define a kind of modified plaquette term like this. So that my B P M. So there's a superscript M now. Of M. That's acting on a stringnet configuration by inserting this line here that's labeled by M. Well, so should draw it like this. This is equal to this, and I insert this loop labeled by M. Right? So it's the same as before, but instead of inserting a loop labeled by my fusion category, I'm inserting a loop labeled by my my module category. Well, this M is going to be a, so M is invertible C D for the by module category. So it satisfies all these properties that I mentioned before. In particular, there's an inverse for this by module. So what's not hard to see now is that if I define BPM as the sum over dm over dim of C times B D M curly M, sum over M. So I'm again doing the same, I'm taking a weighted superposition over these things. You might be worried that I didn't really define what it means to have a quantum dimension for an object in a module category. But if I have an invertible bimodule category, there's a way to actually think about quantum dimensions that's consistent. Because basically you have a dual for every object here, there is something in the dual, and you can define dimensions that are consistent. So what's easy to show now is that if you look at this kind of plaquette term, and you act on the plaquette term of C, you end up with this. If you take the plaquette term of D, and you act on the plaquette term of this module category, you end up with this thing again. And if you take the product of this plaquette term with this plaquette term dagger, you end up with the plaquette term in, let's say, in D again. So what this is telling you is that
Maybe
this...
did you miss some
No.
EC inside?
Where? So this, I define this thing here, right? For generic M, but this includes this case of C and D. So I'm defining sort of plaquette terms for C, for M, and for D. I'm telling you this is how they interact, which is easy enough to prove, but I'll leave it as an exercise. So what this is saying is that this BP is an isometry on the subspace of this plaquette term of D, right? Now, this isometry, we can always, I also have this property actually, so BP C dagger BP C is, sorry, is BP C, right? So this is an isometry both on the subspace defined by the plaquette projector G, D of D, and it's an isometry on the subspace of the plaquette projector of C. And these isometries, I can always make them into unitaries just by adding some orthogonal rows or columns to them, right? Any isometry can be padded out into a unitary. And now what you can prove is that if I have a ground state of the Levin-Wen model for C, so I can obtain this by acting with my product over my B of C on some reference state, right? This will generate a ground state of the Levin-Wen because it's a commuting projectable. This just projects into the +1 eigenspace of all my plaquette terms. If I now act on this with product over all plaquette terms of B, P of M, then this thing, so this is a ground state of C. This operator, which is just the product over all plaquette terms, which is something I can do in parallel. So in terms of a quantum circuit, this is a constant tap circuit. This thing is now a ground state of the Levin-Wen model based on D, right? Because if I look at this projector, B of D, this will be absorbed by this thing here, right? So what I've shown here is that there is a finite depth circuit that relates the ground state of the 11-1 model of C to the ground state of the 11-1 model of D, right? And that's what we expect because they're in the same phase, right? I should be able to do this, and indeed, using this invertible bimodule category, I can explicitly construct this. Okay, so with that, finally, I want to get to these tensor network representations, which is kind of annoying to draw, so I prepared it before. So, how do you now build these explicit tensor networks operators that satisfy these equations here? Well, what you start with is the following. You start with a reference state here. The reference state. So I mentioned that. The ground state can be attained by taking some reference state and acting on it with these plaquette projectors. So, in particular, because of these identities here that I wrote above, I can write the ground state of, let's say, D as the product of all plaquette projectors D, P, M acting on some reference state, right? So I can just absorb this into here, and this will give me a ground state of the string model D. So I start from some reference state, but not just any reference state. Let me also insert this symmetry operator, which is some object in the fusion category C. So I just insert some line here. Now I'm going to act with my BP everywhere, which amounts to inserting these blue loops here. Now these blue loops, they are special. This particular weighted sum makes it so that it actually makes them transparent to these topological defects. I just drew this topological defect on the bottom of this circle, but I can also push it above, right? That's easy enough to prove that this is satisfied. And then I use these F moves to evaluate what I end up with. So I use one F move to, well, basically I first use a resolution of the identity to push this to this configuration here. I absorb this red line into this blue line. Then I need to use two of these bimodule associators to get rid of these red lines and to map to this configuration here. And then I need to use 6 of these module associators to end up with this configuration. And now my claim is that this operation here, this is giving you the tensor network representation of the ground state. You can just go through all these conditions here, and you will end up with basically a tensor network that describes the ground state. So basically what I'm saying is that I'm taking this to be some product state. This is some tensor network operator, and some tensor network operator acting on a product state gives me a tensor network state. Right? I know I went through this very, very quickly, but it's really not very complicated. Just go through these steps, and you end up with tensors that satisfy these equations. And so explicitly, how we draw these tensors is as follows. So this is this tensor here. This is tensor A that I wrote there, although I flipped it vertically, but it doesn't really matter. So this tensor here has some substructure, which is basically a tetrahedron. This tetrahedron evaluates to this F symbol here. That's these guys that I used here. Then I have this symmetry operator, which was something here, the symmetry operator X here. For that, I had to use these bimodule associators, and they end up looking like this. So again, this is some tetrahedron, and you evaluate it to this F sum. And then what I didn't draw is what I could have done is you can draw a junction of topological defects like that. And if you go through this derivation, you would find that it evaluates to this. So you find that it evaluates to this left module associator. Whereas these tensors, these symmetric tensors, evaluate to this right module associator. So I know this last part was a bit quick, but this is basically state sum construction, right? This is building the 11-1 ground state from these tetrahedra that you glue together in such a way that they are invariant under Pachtner moves in the presence of topological defect. That's what these tensor networks give you. This is how you derive these expressions. And so what this tells you is that for a given fusion category symmetry C, the way I figure out all the possible ways in which it can be represented as a matrix product operator is I have to choose this module category and then go through all these kind of things, basically. So for a given fusion category C, I choose some module category M, and this allows me to explicitly find a tensor network representation of that symmetry. Okay, so I will come back to these things tomorrow, Friday, I think. I think Bram will talk a bit about a very simple version of this, where you do this for the Tori code. And hopefully that sort of clears up things. But that's everything I want to say about this.
More questions?
Yes?
Is this X living in the Dreamfield sector?
No, it doesn't have to be, because I start from the empty configuration here. So the half braid is completely trivial, so it disappears. So what's
the blue one? I thought the blue one is labeled by object in the module category.
Yes. So what's happening here is that your symmetries, so basically you can think of this tensor network ground state as a TQFT with a particular boundary condition. So you have your operators in the Dirichlet center, and then you choose a particular module category to define the tensor network representation. And the symmetries that you end up with are basically taking Z of C and condensing them onto this boundary, which leaves you with, well, you have Z of D, basically. You choose a module category M, and then this module category, because it's a CD bi-module category, you end up with symmetry operators labeled by C. That's what's going on. But I don't have to use objects in the center here, because I'm starting from this trivial configuration, which these half braids are not needed, right? I can freely move this however I like, because these are sort of trivial objects anyway. Right? So I don't have to use the center here. It's an important distinction, yeah.
Okay, I think you've already answered it.
That's okay.
If I start from the spherical fusion category, and I view the problem constructing the A.
Yes.
Is it possible to say conceptually what A is in terms of the category?
So this A here would be this thing here. So if you tell me I start from some spherical fusion category, what I would have to do to construct all possible A's is I would have to find all possible module categories, which is for many things have been classified. And then these A's, they are built from these tensors here.
It's really the problem of finding these F's for the module category.
Exactly, yeah. Which is, okay, it's a tricky problem numerically, but it's been classified for many occasions. And so, maybe to comment, if I take as this red thing to be vec G here, and I take as my module category, I take vec, then these guys will turn out to be rep G, because that's an invertible bi-module category, and then these things are the Clebsch-Gordon coefficients. And that's what we know. That's the statement I said at the very beginning, that if we're looking for Hamiltonians that commute with a certain symmetry, they have to be built from Clebsch-Gordon coefficients. That's this statement here. And so what this is giving you is for a general fusion category, telling you how can it be realized as a matrix product operator, i.e. how can I realize it on the lattice, and what are the Clebsch-Gordon coefficients for that symmetry, which allows me to define all possible tensors that commute with it. And so in the next or the last lecture, I will then use this to construct Hamiltonians with these kind of symmetries, and we will see how this relates to gauging these kinds of symmetries in this language, which will allow us to do a bit more.
Okay, so the information of F and the information of A are the same?
Yes. Yeah. So
once you fix the module.
Particularly this guy, indeed. So if I fix, so this guy is this A, so I have to fix this fusion category D, which is not quite the symmetry category, it's a Morita equivalent to it. And then I ask what are all possible ways to find tensors that satisfy these pulling through conditions here. Where did I put them? There. This pulling through condition here, if you fill out these tensors, it becomes the mixed pentagon equation between this guy and this guy. So all these consistency conditions that I have here, this one, this one, this one, and okay, there's another one that I didn't draw. They become the pentagon equations of these kind of things. So this is how you see that these F symbols basically solve those conditions for you. And it's hard to find solutions to these equations if you don't know anything about them. But many of these things have been classified already. So that's kind of where we use these things.
No, this is very helpful, but does this in some sense explain why these A's are so useful?
Yes, yeah. Well, okay, our use for these things is we would just want to understand what are symmetries in quantum systems, right?
I thought you also wanted to understand ground states of these various
Yeah, that's the final lecture where we will talk about exploiting this kind of structures to efficiently compute ground states of the boundary theories of these things. Yeah.
Is the module category labeled the internal lex of A?
Yes, it labels the entanglement degrees of freedom. So the physical degrees of freedom here, these guys, they are home spaces in the Fourier category D. And then these auxiliary legs here, which are these entanglement legs, right? They are home spaces in the module category. Yeah. Exactly. So they determine the entanglement degrees of freedom of these. Yes?
A very stupid comment, which maybe you mentioned already. So this categorical Morita equivalence, it only holds if it holds both ways, right? So you have the composition C, D, C, and the bottom part, but it also has to hold the other way around.
Yeah, I think if you have this and you have that they have the same Frobenius per own dimension, I think that's enough.
Because there are certainly, I think, instances where this holds from one side but not from the other
Yeah,
side.
of course, indeed. Like if you take this to be bigger than, if you take this to be bigger than this, but then the additional requirement of requiring the Frobenius per own dimensions to be the same is like saying, okay, it's a square matrix that's injective, which means it has to be invertible, right? Yeah.
Okay, then let's thank once again.